Okay, well, thanks for joining us. I think we're going to follow up again this week as we're talking about our different generations of refrigerants. We want to cover HCFC refrigerants, so hydrochlorofluorocarbons. And with hydrochlorofluorocarbons, we've got a few very familiar ones. We've got R22 that we've seen for a long time. We've got, if you've been into the commercial refrigeration, you've seen 409 out there before that we used as an interim replacement with some R12 systems. The most common one you're going to find, though, is that R22, because most of us have grown up working with R22, right? Used it for residential air conditioning. We've used it for medium temp refrigeration systems. So I'm going to take a quick poll here. When did we develop R22? Because it's been around a while, but how long has it actually been around? So let me grab this poll real quick. We'll launch that and see if we can get some ideas. Was it 1935, 1945, 1955, or 1965? Got to think about that one for a little bit. How long have we actually used? All right, that's pretty interesting. So survey says 1965 is the dominant answer there. Well, when we look at HCFC refrigerants, we have to understand when they came about and what they were actually getting used for, right? So as that demand in chlorofluorocarbon refrigerants increased, we really got into developing a variety of different chemicals. And we can actually see that by 1935, we were actually producing R22. 1935. The most common refrigerant that we were using was our CFC R12. It was just the dominant refrigerant of its time. It had so many applications that it could work under. It was a medium temperature refrigerant, so it did a lot of cooling capabilities. We developed R22, but R22 is actually a high temp classification, so it is really only practical for residential comfort cooling and refrigeration systems that are maintaining 40-degree boxes or so. So it's not good for a lower temperature application. So it was developed in the 1930s. It didn't really take off though until the 1950s. So it was being manufactured right at the same time as the CFC refrigerants. It just wasn't as popular. But by the 1950s, man, our desire for air conditioning, comfort cooling that we know just multiplied. I mean, we were building heat pumps back in the 1950s. A lot of people don't realize that, but GE was building whole house heat pumps in the 1950s. And we were powering those typically with R22. And so as that demand for larger capacity residential air conditioning systems, because remember by the early 1930s and into the 40s, we were making some comfort cooling devices for homes, but most of them were small stationary units that you would put in the house, or they were a window shaker or a unit that sat in front of the window and had a tube or a adapter so that you could discharge out a window. You could discharge your condensing side out the window. But we didn't have whole house air conditioning systems and really until the 1950s, and then it just exploded. So by the 1950s, R22 just became the dominant refrigerant across the industry because of its comfort cooling capabilities. So if we go all the way back into the 1930s, really it started in 1928 when Thomas Midgley was developed these CFC refrigerants and HCFC refrigerants. So at the time, he was working under Charles Kettering. So when you do a lot of Google search, you'll find information on Charles Kettering as being the founder, the developer of the CFC and HCFC refrigerants. And he was the head of the department, and he was a mechanical engineer that was his forte, was the mechanical engineering side. And then you had Thomas Midgley working underneath of him that was a dual engineer certification. So he had a mechanical engineer and he had a chemical engineering degree. And so he was the chemical engineer that was the driving force behind the refrigerants. He was encouraged by Kettering and they worked together, but it really was Midgley. And Midgley was an interesting person when it came to chemical developments in our early stages of our modern industry. So he actually came up with the leaded gasoline as well. So not only was he working with refrigerants, he was working with all sorts of volatile chemicals because it started with these pre-CFC refrigerants. And so he developed these CFCs and HCFCs to replace the toxic, inflammable, caustic chemicals that we were using, and it revolutionized that industry. And so did the leaded gasoline revolutionize the industry in the time. It took the knocking and the pinging out of the engines that we were developing. So he had his hand in a variety of different chemical changes. And consequently, he developed a persona of being the man that produced the two most dangerous chemicals of our lifetime, CFCs and leaded fuels. And it's sad because at the time they were revolutionary changes in two different industries. And it was science that was so far ahead of its time. It changed the course of our industry and our comfort cooling and our transportation. But it did have some negative consequences down the road. So although he did develop personas of creating those hazardous chemicals, he was a revolutionary chemist of his day and really left a legacy that we are still looking at, still making changes from, but he was the chemical engineer that developed the means of comfort cooling that we have today. So in those original HCFCs, we had a variety of refrigerants that were co-partnering with CFC refrigerants. And we'll also see here, we'll probably see it here in a minute, we also had some that were blends of CFC and HCFC refrigerants. But R22 was really the only one that stayed in the HCFC classification its entire life as a standalone refrigerant. Everything that followed after that was some type of a replacement for a CFC refrigerant. So we were trying to blend and make new refrigerants that were hopefully more efficient than some of these CFCs, and R22 was really the only one that stayed there as it was. So when we look at the early CFC refrigerants and HCFC refrigerants, we'll see that the primary culprits were R11, which we used in chillers primarily, R12 that we used in automotive air conditioning, domestic air conditioning, commercial air conditioning, domestic refrigeration. It was really the primary candidate. It was a medium temp. Both of those were A1 refrigerants. We had R22 that was being manufactured at the same time. That was HCFC that was a high pressure refrigerant, also an A1, so non-toxic, non-flammable. We did have R123 in there that was being used in commercial chillers. That was a HCFC refrigerant, had a B1 classification. And we had R502, but it was a high pressure. Now the R502 was actually a blend of CFC and HCFC refrigerants. And that got used in low temperature commercial applications, but it was a high pressure refrigerant, but an A1. So that was really the refrigerants that we were focusing on in our CFC and HCFC refrigeration phases. What we found as we started getting comfortable with CFCs and HCFCs, we started seeing a trend worldwide. We started seeing a change in our atmosphere. We started seeing an increase of ultraviolet radiation. We started seeing an increase in skin cancers, and we started looking at the reasons for that. And what we found was we had a very significant decrease, which we talked about last week, in the ozone layer. So we had a situation where our oxygen atoms were being pulled apart from our ozone molecules in the stratosphere. And we found that chlorine was the culprit for that. So we started looking at ways to decrease the amount of ozone destruction. So in the 1980s, we came up with the Montreal Protocol, which was an effort from a variety of nations around the world to reduce the chlorine refrigerants that were destroying, chlorine in general, that was destroying our ozone. So it was an international treaty designed to protect the ozone by phasing out the production in a variety of different substances, not just our refrigerants, but these CFC chemicals and HCFC chemicals. And we were going to find alternatives for that. And we were going to reduce the use, and we were going to reduce the manufacturing, the production of these different refrigerants. So we did that. So into force on January 1st of 1989, And there's been a few changes, updates, and revisions to that along the way. The most commonly recognized one is the Kigali Amendment of 2016. So what we've done is we've helped the progression of the reduction of destruction to our ozone along the way. And what we see that there's been a variety of different ways that we have changed the destruction of our ozone. The most important one has been this Montreal Protocol. As you can see, it's been in effect since 1989 and primarily through 2013, and has reduced the annual emissions by 5.6 billion. So now we're getting into, metric tonnages. If we look at all the other changes that's happened along the way, we'll see different renewables that have affected that. We have seen different changes in the collapse of USSR and emissions, US vehicle emissions, deforestation efforts in Brazil. So we've been doing a variety of things to increase the stability of our ozone. But the biggest factor along the way has been our Montreal Protocol and the removal of CFC refrigerants and HCFC refrigerants from our atmosphere, particularly our stratosphere, because our atmosphere is very thin on Earth. If we look at this picture of Earth, we can see the mass that is encompassed within the planet and then the very small atmosphere that surrounds it. And as we get closer, we'll see that there is definition in our atmosphere, and it can be noticed. When we're looking at a horizon, you can actually see where the stratosphere lies within our horizon. So you can see the upper atmosphere up there in the shaded blue areas, and you can see the stratosphere, and then you see the troposphere. So that stratosphere is really where we've been doing our harm. That's where we've been destroying the ozone molecules in that section of our stratosphere. So ESCO is, they work hand in hand with the Environmental Protection Agency to educate technicians on the effects of refrigerants in the atmosphere. And that's why we have our Section 608 license. And if you don't already have your 608 and you're in the industry, we have an entire series that we did last year on EPA prep that goes through all of the things that you need to do to prepare for your EPA license. And it's really all focused on understanding how refrigerants affect the atmosphere. So we find the two primary chemicals that we have focused on because of the Montreal Protocol are chlorine and fluorine. So we know that chlorine affects the ozone, and now we can look at fluorine as a factor as well. And we're going to be talking about that more as we go forward. So refrigerants that have a lot of chlorine and fluorine had to be reduced and removed from our refrigerant lineup. So the very first one was our chlorines. So that was our chlorofluorocarbon refrigerants and our hydrochlorofluorocarbon refrigerants, because of the way they destroy the ozone molecules by removing oxygen atoms from them and breaking up their molecular composition. So we talk about this a lot in our EPA class, and we know that it is from chemicals that we have produced. So in the Montreal Protocol, one of the statements made about that was from President Ronald Reagan, stating that the Montreal Protocol is a model of cooperation. It is a product of the recognition and international consensus that ozone depletion is a global problem, both in terms of its cause and of its effects. The protocol is the result of an extraordinary process of scientific study, negotiations among representatives of the business and environmental communities, and international diplomacy. It is a monumental achievement. So it was finalized in 1987, went into effect January 1st of 89, and we have been designing all of our refrigerants since that point based on that, the removal of our CFCs and HCFCs. So we started doing that, and by 2003, we had a ban on our production and import of 141B. We also started looking at our HCFC R22, 2010, no production or import of R22 by 2010, and a international restriction in production of R22 and 142 in 2020, which we've already seen. So that brought the consumption of R22 down 99.5% of its original calculations. And so by 2030, there is no production or import of any HCFC refrigerants worldwide. So they are on their way out the door completely. and rightfully so. So the early estimations of where we would be with and without our Montreal Protocol was this. We looked back in 1980 and we measured the atmosphere. We looked at the hole in the ozone and we started making calculations based on Dobson units of total ozone. And we found that looking at the track rate, if we did not significantly reduce chlorine and CFC and HCFC refrigerants in our atmosphere, that we would have nearly removed our stratosphere by the year 2060. So in the 1980s, we were looking at 80 years from now, we may not be able to inhabit the place that we live in if we don't make significant changes to our entire world. And so we did that as a world. We created the Montreal Protocol. We phased out CFCs, HCFCs, and we prolonged our time in this planet, and we prolonged our ability to reject ultraviolet radiation. And so now we're looking at more steps to move even further than that. So the EPA has set out standards that we go by for understanding the refrigerants that we have and the refrigerants that we can replace them with. And with that link, if you go to the EPA's website, which is epa.gov, then we have a variety of phase out scenarios. And I encourage you to go check this out sometime, some really good information. So in this, we can look at the different refrigerants, and like today, we're just focusing on the phase out of HCFC refrigerants. And then we can dive into the variety of refrigerants that are replacements for those. So if we look at the phase out framework, we can look at an entire outline of where we're at, where we came from, and where we're going with refrigerant phase outs. And we also have some very good links that talks about the refrigerants themselves, significantly new alternatives policy. So the SNAP policy is what dictates what refrigerants will be acceptable for any replacements. So not just with our refrigerant systems. You got to remember, CFC chemicals and HCFC chemicals are not just limited to the air conditioning and refrigeration industry. We use those for adhesives, we use them for aerosols, we use them for cleaning solvents, fire suppressions, we use them for sterilants, we use them for chemical tobacco expansions. So the entire world has different applications for these chemicals. So we work in the refrigeration and air conditioning, but we can also look at fire suppression systems and what we have done to end the use of different refrigerants and where we have given chemicals that are acceptable or not acceptable for the replacements. So if we have a system that has a CFC or an HCFC refrigerant in it, we can then find the acceptable replacement chemicals that go along with those. Whatever type of appliance we're working on, we can find what the plan is for those particular appliances. So let's take a look at refrigerators and freezers real quick. So in the past, we've used a lot of R134A. 134A is now off from our list of acceptable refrigerants. It is unacceptable in new equipment as of January 1st, 2021. A lot of people didn't realize that. We have phased out R134A in domestic refrigeration appliances. And so now we're going to be using replacements for that. And there are some common ones like R290, which has acceptable with use condition limits because it is an A3 refrigerant. We have R600A, which is another, let me get way down, look at all these different refrigerants. And remember, a lot of these are blends or are now exempt refrigerants. So isobutane is an acceptable with use conditions. So we have to look at the actual rule that is detailed along with that, but it is an acceptable replacement for R134A. So most residential refrigeration systems, residential refrigerators and chest freezers are now coming with chemicals like R600A and R290 instead of the 134A that we were previously using. And we'll talk about R134A a little bit next week when we get into our HFC refrigerants. So a lot of changes in our industry, primarily based on chlorine and fluorine. And we're going to have a variety of refrigerants in our industry that will be replacing even the ones that we know today. So any questions on HCFC refrigerants while we're here? Okay, well, I appreciate everyone's time, and we will see you again next week on Flex Train when we talk about HFC refrigerants. Everybody have a great day.